So this is recitation problem number 4, I think. Yeah, recitation problem number 4. So basically we're looking at transverse waves. We're told that there are some waves in a string, and I'm going to make up these numbers. So assume that the speed of the waves, that transverse waves along the string, and let's assume that so here's our string and it's vibrating. Okay. So we're told, right, let's assume that the velocity of the waves in the string happens to be, let's say it's 78 meters per second. And let's assume that the length of the string, right, L, is given by, let's say it's 8.3 meters, okay, the length of the string. And it's got a total mass m of string, right, is given by let's make it 85 grams. Yeah, that's good, 85 grams. Okay, and the problem is we have to calculate the tension in the rope. So here's the tension in the rope. Find tension. Okay, so what equation are we going to be using? Actually, if you kind of remember, right, that if you take a look at the equations for the speed of a wave in a string, right, in a taut string, right, we know that the equation is going to be V is equal to the square root over the tension over mu. T is the tension and mu is the mass per unit length. Okay, what is the required tension in the rope? So we're going to have to calculate for T. So let's solve for T by squaring both sides. So V squared is equal to T over mu. And if I move everything to one side, we get mu times V squared. Now, what is mu? Mu is mass per unit length. So this is mass per unit length times V squared. And so this is going to be equal to mass times V squared over L. So we can plug in the numbers. Now, final step. Now, a couple of things. Now, this grams, right, is not standard units. So the first thing you should do is really convert this into standard units. In this case, it's, so kilograms would be 85 over 1,000 kilograms. Okay. And this is 85 divisible by 1,000 is, bring out the decimal point by 3 points, so 1203, so 0.085 kilograms. But standard units basically says we shouldn't be writing it this way, we should be writing it as 8.5 times 10 to the minus 2 kilograms. So now we're in standard units. So we can start plugging everything in. Meters per second, standard velocity, standard meters, standard kilograms. So our tension is going to be equal to mass 8.5 times 10 to the minus 2. Okay, mass over the length happens to be 8.3 L, and V happens to be 78 meters per second, so 78. I don't know why I didn't convert this into standard units. Anyway, squared. And let's bring out our calculator. (8.5) exponent to the 2 minus divisible by 8.3 multiplied by 78 squared gives me a value of 62.3. Oh, I'm not going to do it again. sure. 8.5 exponent to the 2 minus divided by 8.3 multiplied by 78 squared. So I get 62.3 and 3 significant digits, but those 3 significant digits are dropped down to 2 significant digits because all the numbers are 2. So this is equal to 62 standard units, newtons. So I made a mistake there. I was thinking T was a time. It's not. It's actually tension. So newtons. Okay, great. So this is problem number 2, part A. Part B, calculate the wave speed in the string if the tension is 8.0 newtons. What? Calculate the wave speed if the tension is 8.0 newtons. Actually, I'll make up a different number. So now the problem is change the tension. So our tension originally was 62 newtons. Now we'll bring it down to, let's say, 12 newtons. So the new tension is given by 12 newtons. And so we have to find the velocity. So we have an equation already, so I just have to substitute everything in. So let's call it T2 just to make sure we're not looking at the same thing. So looking at this equation, right, we can actually continue and say the tension in T2 divisible by mu is equal to V squared. So this means that V is equal to the square root of T2 over mu, which is the original equation. But mu is mass per unit length, so T2 divisible by mass per unit length, which in this case happens to be, running out of space here. Second tension divisible by, multiplied by L, divisible by mass. And so finally I can just substitute everything in. So I'll put a 1/2 for square root. So second tension is 12. And the length happens to be 8.3 meters divisible by the mass. Mass is 8.5 times 10 to the minus 2 kilograms, standard units, and we should get ourselves a final answer. So here is okay, so 12 times, I'll put a parentheses, 12 multiplied by 8.3 divisible by 8.5 power 10 of 2 minus, close parentheses, to the power of 0.5 gives me 34.2. So 34.2 meters per second. And we should double check, make sure the idea is correct. So the actual velocity earlier, right, was 78 meters per second, and we got a tension of 62 newtons, but we dropped the tension to a lower value, to 12. Do you notice that if you lower the tension, the velocity drops? In the case, we got 34.2 meters, and which is smaller than 78, so it looks kind of right. Okay, so this is problem number 4, with different numbers, of course.